I was comparing some cheap LED lamps recently, identical looking LED lamps, but on some of them, the economies that they've gone to save just a few pennies is ridiculous. Take, for instance, these two lamps. This one comes in a pack from the local supermarket, 4 lamps for £5 or £6 depending. Rated theoretically 9 watts, actually measures at 8.5 watts. And this one comes in the local pound shop. That's the equivalent of an American dollar store. And you buy them individually for £1. And this one is supposed to be rated 6 watts, but is actually showing a power of 6.3 watts. But when you open them up, you miraculously, I'll show you how to do that later on. When you open them up, whereas this one has 17 LEDs in it, this one has just 5 LEDs. That is going to really push those. That's more than a watt per LED. In fact, hold on, let's get the Kink Calculator and let's work this out. So here's the Kink Calculator. This one is dissipating 8.5 watts, 8.5, and we'll divide it by the number of LEDs, which is 17 LEDs in this one. Gives roughly half a watt per LED. That's still quite a lot for these tiny little LEDs. This one, on the other hand, is dissipating about 6.3 watts divided by the 5 LEDs. And it's roughly 1.26. It really is that, like, these LEDs are being really pushed hard at 1 watt. So let me show you the circuit boards up close because there's something very, very interesting. So I shall focus down on this like that, and I shall zoom in on this so we can take a look. And the first thing you notice in this is the similarity. They are the same circuit board, not just the same circuit board. They are from the same manufacturer, and they have the very similar codes. It says E309772, E309772, HY6, HY8. Not sure what that bit is. But when you read this number up here, A60Y3, A60Y3, 1570, 2835, which is the size of the LED, 2835, and then this one says 5S1P. What that means, it's a common terminology for the LEDs. It means there's 5 in series. The 1P means it's just a single circuit, because if it said 2P, there might be if it was a 5S2P, there'd be 10 LEDs. There'd be 5 in series and then another group of 5 in series, but fed in parallel. This one, on the other hand, says 17S1P, just a single circuit again, and it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 LEDs all in series. Other slight differences between these. Identical chip, the capacitor in the smaller lower power one is 3.3 megafarad versus about 5.6 megafarad. The inrush resistor is 31 ohms, standard rectifier. That's more or less it. The only thing they've really done here is they've changed the value of the sense resistors to match the power rating of the lamp. Now let me show you something. Let me show you the schematic in this. My apologies to regular viewers, you'll be getting terrible deja vu because I've been looking at a lot of these lamps recently. But it's important to do so because the circuitry has stabilized and it's very interesting what you can do with them. So the circuitry looks like this. We have the incoming supply with the live center contact, or just one contact from the bayonet cap type holders. If it's Edison screw, it's usually down to the end contact, which is, in the UK, this is supposed to be live and the outer shell is supposed to be neutral. I guess that's the same in other countries, but that doesn't happen with adapters. However, I digress. There is a 30 ohm resistor. It has 2 primary reasons. One, it's an inrush limiter, which allows the circuitry to stabilize, and it's also a fusible resistor, so that if something goes horribly wrong, if this goes short circuit, it will pop that resistor while sort of semi-limiting the current, and it won't be too dramatic. So the power comes in through that resistor, gets rectified by the bridge rectifier. That is the little 4-pin package down here. It gets smoothed by the capacitor that is underneath this contact. These are 2 push-in connectors. The reason they've used the push-in connectors is just to make it easy to connect the wires to the lamp, and also to keep the capacitor, it's more reliable if the heat's not covered in the capacitor. So it's just basically just shoved in the back of the housing. In fact, I think this little slot here is an indicator for the negative side of the capacitor so it gets put in the right way around. It could be wrong. It might have some other function. Maybe it's a little vent hole, although they could vent round the actual connectors as well. There is also, after that, smoothing capacitor, which is important. This bit kind of stops it being dimmable, but it does mean it doesn't flicker, which is kind of more important in a way. After that, there's a 1.5 meg ohm resistor here. That does a couple of things. If you're messing around with these lamps at discharge capacitor, you can get quite a zing off that. Even if you've had it unplugged for a while, with this resistor out the way, the LEDs will gradually fade down, but there's a point they won't conduct and it'll still leave a charge of over, well in the UK, over 200 volts in that, and that hurts if you stick your finger on it. I've done it. But the other thing it does, it puts a slight load, because the LEDs are so ultra sensitive that even a few microamps of electrical leakage through switch wiring means that they'll glow. And this resistor clamps that down. It puts that tiny bit of a load that just stops them nuisance glowing. After that, we have the SM2082, which actually contains 2 regulating circuits, but only half of it is used. Keep in mind that the original circuits for driving these lamps had all sorts of fancy switch mode power supplies in them. This, let me see if I can find something like that up here. No, I've completely failed to find something like that. I'm regretting it now. Hold on, I'll open this. I shall open this and show you what would normally have been in a lamp like this. It would normally have been, this is where I regret this. It would normally have been quite complex circuitry. It would have been the little transformer, the switching chips and the smoothing capacitors and stuff like that. And it would have just been a lot more complex. Instead, they've got this tiny little chip that actually goes on the board with the LEDs themselves. And it's not just limiting the current to the LEDs, it's also sensing the temperature of the circuit board. If the circuit board and the LEDs get too hot, it will regulate the current down further to protect them. But they are being grilled. They are being absolutely destroyed in these lamps just because it's cost balancing. They want them to fail quite quickly. That's all there is to it, is they are designed to fail. But anyway, the current flows through the LEDs, and each of these LEDs is more than one LED. To make up the local main supply voltage, which in the case of the UK will be 240 volts, it gets full wave rectified and smoothed, so it goes to the peak of the sine wave, which is about 340 volts. In America and other countries with 120 volts, it will go up to 170 volts. They match the LEDs roughly to that voltage, so very little has to be dropped across this current regulating chip. This means that these 5 LEDs here are going to be probably about 40 volts or something across each. I've not tested that. I should test that. I may test that. But it's a very high voltage being dropped across the LEDs, multiple chips in each of those packages. And then the current flows through this chip, and then it flows through 2 sense resistors. The reason there are 2 sense resistors is because they have to be accurate. They accurately set the current that goes through the chip. And it's really, it's not just a case of spreading the load. You could have like 2 100 ohm resistors in parallel. That would make an equivalent of 50 ohms. In reality, what they're doing is they're choosing a low value. In some of them, it's very low, something like 12 ohms. And then they actually put, say, 500 ohms across that. And that just, the huge difference in them means that the 12 ohms is a dominant value. The 500 ohms just nudges it fractionally down. They can fine tune it right up to the edge with those, by having those 2 resistors. It also gives us a weapon for making these lamps last longer. So the way the current is regulated is this chip measures the voltage across these resistors. And the higher the voltage, the higher the current going through the resistors, the higher the voltage will be across them. So when you power that on, initially, and this is where this resistor comes into play again, it allows that capacitor to charge up. I was going to say slowly, it doesn't. It's almost instant, but for the circuitry, it might as well be slowly because it can react in time. As the capacitor charges up through that resistor, the current starts flowing through the LEDs and those resistors. The voltage goes up. As soon as it reaches 0.6 volts, this turns into a little electronic resistor and limits the current down to the point that that hovers accurately at 0.6 volts. What's in here is just basically a couple of transistors and some extra circuitry that forms a simple current regulator. But it means that you can change these resistors and you can make that lamp any power you want. So say, for instance, this lamp that is absolutely baking these LEDs, you could turn this into a 1 or 2 watt lamp. If you, say for instance, in the UK, if you put a if you want to turn it into a 2-watt lamp, you could replace those two resistors with a 100 ohm resistor, and it would regulate down to approximately a 2-watt lamp. That would then take the strain off these, and they'd last a lot longer. You can, well, I've worked out loads of values here. This is this is going to give the same sort of current, no matter whether it's a 120 volt lamp or a 240 volt lamp. But in the America or other countries, they may have those other LEDs in parallel, which means you'd end up needing twice the current to actually to get the same sort of level of power. It's just it's balanced to the local supply voltage. To work out the LED current, you divide the 0.6 by the resistance. And if you want the power, multiply the 340 volts up here by the current that you actually calculate from dividing the 0.6 by the resistance. So here's an example. In the case of this one, we've got 56 ohms and 43 ohms in parallel to make 24 ohms. If you want to calculate this, a couple of things. The circuitry doesn't load it down that well. Let me bring a meter in and show you this. The circuitry doesn't load it down too much, so you can just use your meter and you can measure those resistors in parallel like this. So that's about 24 ohms. Let's see how accurate we get to this. This meter has removable probes. They screw in so they can be replaced. They keep unscrewing. So if I put this across, I'm expecting a value of about 24 ohms. What I'm actually getting is 24.6. So you can measure across these with a meter quite accurately. And there's a really simple calculation you can do. If you take your resistance and you multiply it by the power the lamp takes, then you can actually hack this. I've shown this in other videos, but it's worth showing again just because it's interesting to do it, particularly to the cheapy Poundland lamp. Well, let's do it with the Poundland lamp. So this one is at 82 ohms and 51 ohms. That gives a total value of 31 ohms. If you multiply the 31 ohms, where is that one, by 6.3, let's bring in the Kink Calculator and do that. So multiply the value in resistance, 31 ohms, times, and the power that it measures at, 6.3 watts. 6.3 watts gives you a figure of 195.3. Hold on, I'll write that one. 195.3. 195.3. That number is just a sort of a midpoint in the calculation, so to speak. If I then decide I want to reduce the power of this lamp, now I could either use I could either keep the 51 ohm resistor or the 82 ohm resistor, or just add a resistor in. If you divide this figure, 195, divide it by the 51, divided by 51, it will turn the lamp into a 3.8 watt lamp. If you 195.3 divided by, this is what I'm tempted to do, the 82 ohm resistor, it will give you a 2.4 watt lamp. Shall we put that to the test? Let's put that to the test right now. So I'm going for 2.4 watt. Let's see how close I get here. This could all go horribly wrong. Maybe my calculations are terrible. I don't know. So here's the lamp. I'm going to keep the 82 ohm resistor. I'm going to get rid of the 51 ohm resistor. And that's this little one here. I'm going to just go into the snips and I'm going to break that off. I'm going to try and break it off. Maybe I won't break it off. They're soldered very close together. It's unfortunate that because these are aluminium heat sinks, they don't, they're very hard to solder on. But you can break the resistor off as I've just done. Let's measure that. Let's zoom out. The regulars will be sick of these LED lamps by now because I've just been doing too many of these recently. It's my latest thing and I'm doing it to death. So here's the lamp going into the socket that I've hopefully converted into a 2.4 watt lamp. Let's put the cover on it. Click the cover on. 2.48 is pretty good. I think that's fine by my standards. That calculation has worked out perfectly. So the nice thing is, right, these lamps are from the same manufacturer. They've just been tweaked to last a certain length of time and cost a different, I mean, does it really cost, are they really saving that much money with using the 5 LEDs versus with the higher voltage versus these? Because, you know, £1.50, £1, there's not that much of a difference. And these ones are really absolutely roasting the LEDs. But anyway, I digress. Let me show you how to get the cover off these lamps. I'm using an Edison screw one for your viewing pleasure, so that people in Edison screw countries, and that's not just America, that is a lot of Europe as well, will feel comfortable. Most of these lamps have the plastic globe. You can squeeze them very gently, but be very careful, some are still glass. Just be careful about that. If in doubt, wear gloves. Don't use a sharp knife for this. This is a spudger. It's relatively sharp, but it's not stab yourself type sharp. You can either, to get these off, you can crush them completely, but if you want to save them, as has been suggested many times, take the spudger or your sharp blade and just slide it down into the side of the lamp. And some of them it's easy, some of them it's not. Once it's slid in, just slide it round like this. And it's glued solidly in there. Once you get it off, well, there, it's the same brand of lamp. Let's zoom in this. This one has 56 ohm and 43 ohm. It's pretty much the same as this lamp here, but with just a different base. And again, if I wanted to, well, let's do it. Let's do the test. Let's zoom back out. Now I've opened this one. How long before the lamp manufacturers take the hump at what I'm doing here, and they modify the lamps in some way that stops me doing this to them? All big class fans are making the lamps last forever. So let's put this lamp back together, right? This is the supposedly a 9-watt lamp. Let's put the cover back on it, plug it in, and look at the hoppy. It's 8 watts on the button, right? So 8 watts on the button. What can we adapt this to? So I've unplugged it. Let's unscrew it. Keep in mind, if you're doing modifications like this, that the circuitry in here is all live at mains voltage. Just so you know that when it's actually plugged in. So we've got the 43 and 56 ohms. Let me go the full hog here. Let me do it like the proper way. So here's the meter, and I'm just going to bridge the capacitor out here just in case. I think it will be discharged. Yes, it is. So that's the 43 ohm and 56, is it? In parallel. There are calculators you can find online. That's the 24 ohm, right? So that's the 24 ohm resistance. So let's say 24.5, Kink Calculator, 24.5 times the rating, which was 8 watts, equals, that gives our base number 196. That's very similar to that. I'm thinking 196 might be the magic number for them all, for the UK lamps. That's useful to know. I've just made that connection right now. Okay, so that will be based in the 0.6 volts and the peak of the sine wave voltage. That's interesting. That suddenly makes sense now. So I've got the choice of the 43 ohm or the 56 ohm. I'm going to keep the 56 ohm. So I'm going to divide that by the 56. What am I going to get? I'm going to get 3.5 watts. Will we put that to the test? Will we do that right now? Let's just get this resistor out of there. Probably side cutter abuse here. Get out resistor. As I say, you could desolder these and you could solder in custom resistors, but these circuit boards have an aluminium core to help them dissipate the heat from the LEDs, and it makes them extremely hard to solder. Okay, that's it. As long as I've not damaged the resistor next to it, it should be fine. So this should be 3.5 watts. Will we test that? Let's screw it in. Put the cover back on, just to prevent glare. And then 3.5 watts, 3.6 watts. Pretty close, huh? And that now is going to run super cool, and it's going to last for ages, but it still puts out a good amount of light. I have to do the test where I test them at loads of different power levels and then actually see what the light output is, because theoretically they get a lot more efficient as the LEDs are not overdriven. Now there's one other thing I can do with this. Let's get the Poundland lamp, and I'll show you how to fit in the crystal. I've got a crystal here, and I'll turn it into the diamond lamp. This is a kind of merging with another video now, where I printed loads of different lamp caps like this, 3D printed. This one is done at 0.2mm thick. This one is done at 0.3mm. You can see that this one is clearer, but each has its own sort of style, each sort of look. And these are sized to go basically into that. Oh, there we go, it's in. Yeah, right, okay, I maybe should have tried that before. I don't know. Right, plug it in. So this is the doctored Poundland lamp with this lens, this diamond lens that can be glued in now. And it's turned it into this really decorative lamp. I'm going to have to grab another one now. Let's grab hold of the big quartz crystal. These are featured in another video that has all the 3D printing files that you need to actually create these and custom sizes. And the quartz obelisk, yeah, look good, doesn't it? That is the cheap Poundland lamp now turned into a decorative lamp that's going to last a good length of time once these are all secured in place. To secure them in place, as I featured in the previous video, get a screwdriver and just go around the outside to remove all the old glue, the silicone type glue, without damaging any of the LEDs. I would say that the other LED lamps, most of the glue has come out here. There's not much in this. I think that's probably because I've probably taken out already. Oops. But most of the... what was I going to say there? The glue, once you've taken it out, put some glue in there and just basically put the cap in, and then I just plug it into a lamp holder and let it cure the glue. I used Yoo-hoo glue, and I just actually turned it on, just plugged it into a lamp holder and let it heat itself up to actually set the glue itself. But there we go. It's so interesting that these are all coming from one standard factory, from the ones from your supermarket, the ones from the dollar stores. I think Adrian at Adrian's Digital Basement a while ago, he featured one of the dollar store lamps, and it was so similar that they must all be just standardizing in these non-dimmable, wham bam, you know, low efficiency, high temperature, short life, generic lamps. They are the replacement for the standard tungsten lamp. But there we go. Interesting stuff. So that's how you take your pound shop lamp and yeah, convert it. But to be honest, having seen that this one's got this one for 50 pence more, I'd say maybe go for the supermarket lamps instead. They're going to be a lot better that way. And if you want to fine tune further, if you want to get down as low as it can go, you can go down to 1 watt with these if you want a low level decorative lamp, by putting that 200 ohm resistor across the position of where those two resistors were. But you're going to have to solder for this, and it's going to take a bit of effort because of the aluminium taking the heat away. But if you do that, it's going to let you hack it into a decorative lamp that will probably last forever. It will literally last, you know, 10 years maybe, because there's no real stress in it. And the lower current also means that the capacitor in here is running cool. It's going to last longer, and the capacitor is rated for the higher intensity, so it's the ripple is going to be less as well. It's like a win-win situation. But there we go. Interesting stuff.